Hello, in this video I will talk about visualizing determinants, in particular 2 by 2 determinants, and that will justify the way we defined determinant. So if you have a 2 by 2 matrix A, B, C, D, determinant of that matrix is defined as A times D minus B times C. So why do we define it in this way? So I will discuss about visualization of this definition, and also you can then generalize to 3 by 3 determinants, and the same geometric idea lies behind 3 by 3 matrices, even though 3 by 3 determinants, even though 3 by 3 determinants seems to be much more complicated to define. So but it's behind the same basic geometric idea is behind the two. In order to talk about determinants and what their geometric meaning is, I will need to discuss linear transformations, and most of the time in this video I will spend discussing linear transformations, and that's chapter 4. So what you will see here is something that you will need for chapter 4, and I think it's worthy discussing it. So it turns out that we can represent linear transformations as matrices, and determinants of those matrices are actually measures of deformation under that transformation. So what exactly linear transformation is? So let me give you one typical example. So suppose I'm making pizza and I make a dough, all right, and I want to stretch the dough. So suppose I put the dough on the table, which is my board, and I'm stretching it, and I'm stretching it in this way, so that some points of the dough move to the right and some points move to the left. Now at each y level there should be a point that doesn't go neither to the right nor to the left, so it stays fixed. And suppose that my stretch is such so that it's geometrically perfect, so that the points that stay fixed are actually points on some vertical line, which I will denote by y as y-axis. And also suppose that my stretch is such so that any point of the dough gets moved away from y-axis in a way so that it initially arrives at a position that is twice as far away from y-axis than it originally was. Okay, so this point gets mapped here, and this distance is twice the distance from here to here. This point gets mapped here, and this distance is twice the distance from here to here. And this midpoint, okay, of this line segment, I map it here, all right, so that this is twice the distance from here to here. Now this is a point that I will denote as I can think of it as a vector, or a point that is ordered pair in Cartesian plane, or I can think of this point or vector u as a column matrix, so with coordinates u1 and u2. So this is my x coordinate, this is y coordinate. It's I can identify it with the pair u1 u2 as you are used to do it in previous classes. And so similarly with the vector v or point v. Now what happens with this midpoint? Where does it get mapped? Well, the way I drew this picture, it looks like the midpoint of this line gets mapped to the midpoint of this line. So this is the image of v, this is the image of u, okay? And the midpoint between u and v gets mapped to midpoint between L of u and L of v. Well, why is it really so? It certainly is geometrically plausible, but how would you strictly show that? Well, to see that, you can look at the line through points U and V and think of the line of the slope of this line with respect to y-axis. That's rise over run. So rise over run for this point is the same as rise over run for this point, which is the same as rise over run for this point. They all have the same slope because they lie on the same line. That's the assumption. But you can see that this point, and also this point, being images of these three, actually have slopes 2 times the slope of corresponding point on this line. And so so rise over run here is twice the rise over run here, because simply rise is twice as big. And similarly for these 2 points. And so they all have the slopes twice the slope of corresponding points on this line, and these slopes are the same, so therefore all these have to be the same, which exactly means that this point lie on this line. And so this midpoint here, I can algebraically write it as the average of u and v, because it's a midpoint. So it's 1/2 u plus 1/2 v, and it gets mapped to the midpoint of this line segment. And if I denote by L this transformation, this dou stretching, I will denote it by L, because that will turn out to be a linear transformation. So L is for linear. So L of the average of u and v, so that means 1/2 u plus 1/2 v, is what? It's the midpoint between L of u and L of v. So I have L of u and L of v, and I need to take the average of them. Well, that's actually 1/2 of L of u plus 1/2 of L of v. Okay? Also, a similar thing works for other points. So let's say this point, which is midpoint between these two. So this point is 3 times closer to u than to v. All right? It will get mapped to the point on this line segment that is 3 times closer here than here. Okay, so again, using similar triangles or slopes, you can argue that this guy will be 3 times closer to this point than to this one. Okay, and what is this point here? Well, being 3 times closer to u than to v, its weighted average between u and v is 3/4 of u plus 1/4 of v. So because it is 3 times closer to this point than to this point, this coefficient has to equal, has to be 3 times the coefficient here. And the reason why I divide by 4, well, actually they need to add up to 1, these two coefficients. Why is it so? Well, actually so if you took Calc 3, this is like a question of parametrization of this line, and you should know that in fact any point on the line from through points u and v is of the form theta u plus 1 minus theta v, or actually I should say alpha, to be consistent with notation in the book, 1 minus alpha. So why is this so? Well, take any point, let's say this one. I can also take on this line, but outside this line segment. So maybe here or here or here or here or here or here. So let's say this point, okay? This point, so when I look at this vector from u to this point, Well, that vector is a scalar multiple of this vector from u and v. So it is some scalar multiple of vector from point u to point v, so that's a vector v minus u. And so that's this vector here. And this point here, represented by vector from the origin up to here, is actually the sum of vector u and this scalar multiple of v minus 1. So if I add u, I get exactly this point here. And you see now when you simplify, this becomes 1 minus theta u. So this is 1 minus theta u plus theta v. Okay. Now theta is arbitrary real number, and I can redenote 1 minus theta as alpha. If 1 minus theta is alpha, then theta itself is 1 minus alpha. So that's where this comes from. Okay. So that's a brief explanation of parameterization of a line. And so if I have a point or column matrix, 2 by 1 matrix that is represented in this way, that means that's a point lying on the line through points u and v, or vectors u and v. Okay, and where does its image land? Where is its image? Well, actually, I forgot to say for this special case. So for this point, as I said, if you are 3 times closer to u than v, you will get mapped to a point that is 3 times closer to L of u than to L of v. So that exactly means that the weighted average between u and v that is 3 times closer to u than to v gets mapped to a point that is 3 times closer to L of u than to L of v, which means it's a point 3/4 L of u plus 1/4 L of v. And now it's not difficult to see that it works actually for any two numbers as long, two coefficients, as long as their sum is 1, and that is, in other words, that L of any point on the line through points u and v is equal to alpha L of u plus 1 minus alpha L of v. In other words, proportion of distances of this point from u to v is the same as proportions of distances of its image from the images of u and v. Okay? And so this property is actually line preserving property. It actually means that what is on the line through points u and v gets mapped to something that is on the line through points L of u and L of v. So if you have 3 points u, v, and this one that are collinear, belongs to the same line, when you map L of u, L of v, and L of the third point, they will be on the same. They will be on the same line, as we can see here. In general, there are some special cases when you have some deformation, degeneration that makes points collapse points of the line collapse to some point. But at least in this case, every line gets mapped to some line. And even more, if you take actually arbitrary point, and by arbitrary point I can represent arbitrary point in this way. So let me take this to be arbitrary point, and I will think of this point. I will get to this point from the origin. If I go from the origin to this vector, okay, so that's let's say some point of this kind where alpha is in this particular case 3/4, but it can be actually any point on this line. So from here to here, and add this little vector here. And actually the way I choose this point is so that this vector here is parallel to V, okay? And so this point will be of this kind, and then I add a vector that is parallel to V, so it must be scalar multiple of vector V. And so if I have here a right triangle, if I want to see where this is going to land, it's where does it get the map? So it's somewhere here. Well, from here to here is from here to here is twice the distance from here to here. All right, and so similarly here. This point gets mapped here, and so this distance has to be twice the distance from here to here. But that exactly means that this vector, which is some scalar multiple of V, so let me say it's this vector, so that's the same vector as here, so that's some vector kV, it gets mapped to this vector, okay? So this vector here, well, so it has to, the distance has to double, so maybe, so it's here. So this is my L of kV, it's this point, L of kV, all right? And using similar triangles, so if I connect L of V point with the origin, so that's my vector L of V, this L of kV has to lie on L of V, and by similar triangles, the ratio this over this is the same as this over this. In other words, L of kV is K L of V. So, if instead of letting this coefficient multiplying V to depend on alpha, simply as 1 minus alpha, I can add arbitrary, I can add kV with k being arbitrary scalar, so that this scalar 1 minus alpha plus k is arbitrary and does not depend on alpha, because this guy is free of alpha, does not depend on alpha. Then the image, so I have this point, that's my LU plus 1 minus alpha V plus KV, gets mapped here. But this is exactly, this point is exactly, or this vector from origin to here is exactly sum of vectors from here to here, which is L of just this part, and that's actually this thing, and plus this vector, which is nothing but the image of KV, that is L of KV, but as I said, by similar triangles, that's KL of V. So that means if I add this term KV here, I will also add here KLV. And so now 1 minus alpha plus k, if I denote by beta, what I get is alpha u plus beta v. This vector, that's actually an arbitrary vector in the plane, gets mapped to alpha L of u and plus 1 minus alpha plus k times vector L of v, so that's a beta L of v. And again, beta does not depend on alpha because k is independent. So this, my pizza stretching or dough stretching transformation, or dot transformation, satisfies this property. This is called linearity, or we say that anytime you map a plane into plane that this property is satisfied, such mapping, such transformation L is called linear. And you can now generalize the same identity if U and V are 3D vectors, and this is transformation of the space. Then you have a 3D space. You define a linear transformation in this way as well. Now, what are typical examples of linear transformations? Well, here is one. Computer graphics wouldn't exist without linear transformations, because linear transformations are, say, rotation about origin. So when you rotate image in when you watch photos and you want to rotate, that's a linear transformation. If you want to zoom in image or zoom out with the center point with zooming centered at the origin, that's another linear transformation. And if you play video game, if you are playing some I don't know, video game where you need to move through space, when you want to rotate, you push a button for rotation, and actually all the pixels, all the colors of all the pixels get moved around you in exactly the way that you would expect in real world. And how come that the computer knows how to rotate all the pixels or all the colors of all the pixels? Well, because that is represented by linear transformation. So you see that this linearity, special case when beta is 1 minus alpha, that's this property, and this is line preserving property, so, or collinearity preserving property. So collinear points get mapped to collinear points. And so if a transformation is linear, it in particular preserves collinearity. Now there are some simple transformations of the space that you might think are linear, but actually are not. But and the reason for, usually the reason why it is not is because they don't make origin fixed. This property immediately implies that L of the origin, that is a zero vector, gets mapped to the origin. In other words, you don't move the origin. To see this, just plug in U and V vectors being zero vectors, the origin, U and V points being the origin, and alpha and beta being 1. So you have L of zero vector plus zero vector. Well, that's like L of zero vector. So you have L of zero vector on the left, and on the right you have 1 times L of 0 plus 1 times L of 0, so that's 2 times L of 0. And the only case this to happen for some vector L of 0 is that that vector, or that point L of 0, is actually a zero vector. And so you see that this linearity property does include line preserving or collinearity preserving property, but also requires that the origin stays fixed. And if you have a rotation about origin, that is going to be a linear transformation. But if you have a shift, that is a translation, all the points get shifted by some vector, and in particular the origin gets shifted, so the shift, the translation is not linear transformation. It belongs to a broader group called affine transformations, and actually any affine transformation is line preserving, collinearity preserving, and any affine transformation can be thought of as a composition of a linear transformation and one translation. Okay, so why are we talking about linear transformations? Well, because you can represent linear transformations using matrices, the stuff that you've seen in chapter 1. And actually, that's one way. Linear transformations can be thought of as a way of visualizing matrices. Now, I am dealing only with the transformation of plane into plane. You can also have plane onto line, or 3D space to plane, or 3D space to 3D space, and you will see even more general n-dimensional space to m-dimensional space, but you will see that later. I don't want to broaden the story. So how do we represent linear transformations with matrices? Well, I take arbitrary vector or point u. I can think of it as a row matrix with two components, and I can write it as this real number u1 times 1, 0 and plus u2 times 0, 1. That's just by basic matrix arithmetic. I can decompose it in this way. Now this point 1, 0, that's a point here, a distance 1 from the origin, okay? In our book and many other books, it is denoted by E1, okay? And similarly here, on y-axis, a distance 1 from the origin, lies vector or point E2. And that's actually 0, 1. That's this vector here. So this is U1, E1 plus U2, E2. And I can say that U is a combination of E1 and E2, or in other words, linear. It is said that it's a linear combination of E1 and E2. Now, by linearity of transformation L, so if L is a linear transformation, then L of this, L of U, that's L of this vector. So U1 and U2 are real numbers, and those are X and Y coordinates of this point U. So by linearity, this is U1 L of E1 plus U2 L of E2, with U1 and U2 playing the roles of alpha and beta, respectively. So in the previous story, and you see that if you give me a vector U, in order for me to tell you where its image is under that transformation, where does L of U land, all I need to know is the images of E1 and E2 under that transformation, okay? And I can write this in the following way. Think about block matrices, L of E1, L of E2. Now, L of E1 is a column matrix, 2 by 1 matrix, and L of E2, because those are points, okay? So this matrix actually is matrix 2 by 2, because so both L of E1 and L of E2 are some columns, all right, with 2 rows, times, so this is times U1, U2. And if I denote this by matrix A, it's going to be 2 by 2 matrix, and L of U can be represented. This is just a product of matrices, the way we define it. Remember, it was a bit weird maybe, but you can see in the book some justifications, some examples where this way of defining product of 2 matrices becomes handy. So we have L of U, and here is one such situation, can be written as matrix A times matrix, or that is vector U. And so you see, whatever point U you give me, its image, I can find its image under that transformation. It's actually matrix A times U. So you see, this matrix A contains information about where E1 and E2 land, and just knowing that, I can find you any other image of any other vector. Now, so this matrix A represents this linear transformation L. But it should be clear that this matrix A does rely on vectors E1 and E2. You can represent matrix L with respect to some other two vectors that form so-called bases, which you will soon see what the basis is. So I can take any two vectors that are not collinear, in other words, that they form bases. If, if I define their images, there is only one transformation, linear transformation that send those vectors, I mean E1 and E2, to those images. Okay, so it's completely determined by knowing the images of E1 and E2. All right, and so now determinants. So this matrix A is 2 by 2. Okay, and the determinant of this matrix, which is AD minus BC, actually tells you how much the space was deformed under this transformation. Remember, I had the pizza dough, and actually my pizza dough got stretched. So I should guess that whatever dough was now is expanded, has expanded. By what factor? Well, it's not difficult to see by what factor, and you can look at a unit square spanned by E1 and E2. So here is E1, here is E2. And this is a unit square over E1 and E2. So E1 under this pizza stretching or dough stretching gets mapped here, and E2 stays where it is. This line stays. This line segment stays where it is. This line segment gets stretched here. Remember, lines are mapped to lines. This one gets mapped to this line segment, and this line or line segment gets mapped here. And any point in this unit square gets mapped to some point in this rectangle. Okay, and this rectangle, so this is 2, number 2 on the x-axis. So this rectangle actually is 2 times, so its area is 2 times the area of this unit square. So my original unit square got doubled. And it's not just, there is nothing special about unit square. You can take any small, you can scale it and take any small rectangle, any small square, it will get doubled. And if you take arbitrary area and decompose it as a union of little squares, each of these squares get doubled, and so the whole union, so at least approximately it's a union of squares, but you can now take finer and finer partitioning of this area into squares, and you see, because every square gets doubled, the whole area gets mapped to something that is double the size of the original region, of the original area. Okay? All right. Now, in this particular example, what is the matrix that represents those stretching? Well, remember, this first column is should be L of E1 vector, and this second column should be L of E2. And L of E1, that's actually this vector, so it has coordinates 2, 0. and L of E2 stays where it is, so the image of E2 is E2, that is 0, 1. Okay? What is the determinant here? The determinant is 2 times 1 minus 0 times 0, which is exactly 2. And I told you that this transformation doubles the regions, doubles the areas, and determinant of A is actually that measure of deformation. In this case, it's 2, so that means that you double the area. How can you, in general, see what is the measure of deformation? Well, so how can you, in general, see that every area gets deformed by a factor, in this case 2, and in general by a factor AD minus BC, and that's the reason why we define determinant in that way. So how do you see that it gets deformed in this way? So it suffices to see where the unit square gets mapped, so that so suppose I have here that E1 gets mapped somewhere here. So this is L of E1 and L of E2. So this is my L of E2. All right. So L of E1, that's, so let me now see in general. So suppose we have arbitrary linear transformation. This is the image of E1, this is the image of E2, okay? And how much the space was deformed? Well, the answer is how much this unit square was deformed. In other words, unit square is over area 1. Now, instead of E1 and E2, you have image of E1 and image of E2, and the measure of deformation is going to be the area of this parallelogram. And actually, under linear transformations, you see, in general, you may have square getting transformed into parallelogram. But actually, any parallelogram, this square is just a special case of parallelogram. It's a right parallelogram. A rectangle is also a special case of parallelogram, but any parallelogram gets mapped to some parallelogram. You don't need to preserve angles, but you do have parallel lines being preserved. Okay, so what is this area? Well, if this is my point, so what is that's point AC, so matrix AC, and this is matrix or column matrix BD. Okay, this point here. So just think of the sum of these two vectors. So add the x components. That is going to be x component, and add y components. That's going to be y component of this sum. All right. Now, when you look at, I'm going now to erase this and erase this. When you look at this big rectangle, from here up to here is A, and this is just the x coordinate of this vector, so that's B. All right, so I have here B. Okay, this is A, this is B, and so this is A plus B. All right, so I can express area of this parallelogram as this big rectangle, which is A plus B times C plus D, and then minus all these pieces. So this triangle and this triangle, they are congruent which is a fancy word for the same shape and size. These two guys, this one and this one, they are also congruent. And what else? This is B here. Also, this is B coordinate. This is also B. This height is C, and this height is, this is D plus C, and this is D, so this is also C. So these two rectangles are congruent. And so the area of parallelogram is this big rectangle, which is of area this, minus 2 times this triangle. Well, what's the area of this? So 2 times the area of this triangle. Well, that's B times height is what? What is height? Height is D, the same as this one. So BD divided by 2, this triangle, okay? But it's 2 because I have 2 triangles. Similarly, these two, so this is A times, what is this? This is C, A times C divided by 2, but then I need to double, I have to count it twice, so BC over 2, and I have these two rectangles being B times C, so minus 2 times B times C area. And now simple algebra shows that this simplifies to what? Well, it simplifies to AD minus BC. Okay, so I have AD minus BC. Now there is one more thing. Determinant can be negative, and area cannot be negative. So area of parallelogram cannot be negative. So how do we reconcile? So I told you that the determinant measures deformation, but what if it's negative? Well, it's all about orientation. So what is orientation? Well, so the way I made pizza, or the way I made dough stretched, it's not that I suddenly had a point from here, it suddenly moved here instantaneously. No, I actually stretched it in applying some continuous motion, right? So think of it as a dynamical process, transforming a space, transforming a line, plane. So now let me take an example. Here is E1, here is E2, and suppose I map E1 here. So this is -1 on y-axis. So this is L of E1, okay? So that this is actually what? 0, -1, okay? And I map E2 here. This is -2 on x-axis, okay? And I can think of deformation just like in dough, the stretch. I think of this deformation where this guy continuously gets moved or deformed and sent to this point. Okay, and similarly, simultaneously, while this guy at this point is traveling to here, with the same time, within the same time, this point travels from here to here. So they start moving at the same moment, and this one is going to go faster, and they land here at each one lands where it has to at another time, terminal time. Okay, and at each moment of time, I have them somewhere. So all those points somewhere on the line on these line segments. So let's say if only quarter of time passes, so I gradually or continuously move this point towards this point, and after a quarter of the time it gets here, and after a quarter of the time, the same amount of time, this guy gets quarter way through from here to here. And what you get is some kind of intermediate deformation where E1 is mapped here and E2 is mapped here. And now instead of Now this unit square gets deformed under this intermediate transformation, gets deformed to this parallelogram. And the area of this parallelogram is of course going to be positive, but it's smaller than unit area, okay? And as you move this point along this path and this point along this path, you can see that this point is getting closer towards the origin, and so the area gets smaller and smaller. And halfway through, I will get intermediate step where this is halfway through from here to here, and this is halfway through from here to here, and actually they will be lying on the same line. The images of E1 and E2 under this intermediate transformation, or this one frame, okay? And actually that's where it gets deformed to 0. And now from here you are now flipping. E1 and E2 were on this side of the line, and now they are on the other side. And that flipping can be thought of as a change in sign of the determinant, okay? And eventually you do get that E1 lands here, E2 lands here, and so what is the image of unit square? Eventually, it's going to be this rectangle, and this rectangle, because this is -2 and this height is 1, the rectangle is of size 2. And so that means that determinant is going to be of magnitude 2, but because you flipped E1 and E2 about this axis, which is about this line, which is a line at some so that at some point of time E1 and E2 images got parallel. Because of flipping about that line, you will get determinant -2. And so in general, the way you can think of orientation in 2D, you take point 0, point E1, and point E2. This gets mapped to L of 0, which is 0. That's for any linear transformation. This gets mapped to L of E1. This gets mapped to L of E2. Now, these points 0, E1, E2. Suppose you jump from point 0 to E1 to E2. So in other words, from here, 0 to E1 to E2. So I have this triangle, I jump from here to here to here to here. So this is so-called, so this counterclockwise motion is actually so-called positive orientation. We say that vectors 0, E1, E2 are positively oriented. It's important to put them, so the order matters, okay? If you have 0, E2, E1, so if you flip this, you will go this way, so that's going to be negative orientation. Clockwise orientation is negative by definition. You can call it Thelma and Louise, or you can call it black and white, you can call it plus and minus, whatever. We call it plus and minus, or positive or negative. You can also call it clockwise and counterclockwise. So anyways, but so now when you look at their images, if these three are going in the same rotation as this one was, you do not change rotation. If if these guys go into opposite direction, then these three guys, that you have a change of rotation, change of orientation. So what is L of E1? That's this guy here. So I have 0 to L of E1, so from here to here, and then to L of E2, that's this vector. So I have from here to here to here, here to here. So I'm going clockwise now, which is opposite of counterclockwise. So from here to here, I flipped the orientation. And so that's how you can immediately guess when I describe in words in English. If I tell you what transformation does, you can immediately guess what its determinant is. So let's see for this one, because I double the unit square area, the magnitude of the determinant is 2, and because I flipped the orientation, the determinant of a matrix that represents this transformation is -2. So let's see, let's check. So this business with the AD minus BC, you can see that if I flip the orientation, AD minus BC is going to be negative. Okay, so what is the matrix in this case? So remember, first column of the matrix is going to be L of E1. What is L of E1? It's this vector here, so 0, -1. And L of E2, that's this vector, so that is -2, 0. What is the determinant? It's 0 times 0 minus -2 times -1, which is exactly -2. Exactly that we predicted. Let's see another example. Let's say I flip about y-axis, all right? In other words, so reflection about y-axis, so this vector E1 gets mapped here, that's a minus E1, so that's a -1, 0, and E2 stays where it is. And you know immediately, so you have 0, E1, E2. Now you have 0, -E1, E2. So 0, E1, E2, so that's this, so that's a counterclockwise, positive, so-called positive orientation. But now 0, -E1, E2, so 0, -E1, E2, 0, -E1, E2. So that's clockwise, so that's opposite orientation of this one. So you know immediately that the determinant of this flip about y-axis has to be negative. And what should be the magnitude? Well, the magnitude should be tell you how much it deforms the plane. Well, this square gets mapped here, which is also unit square, so no deformation, so the magnitude should be 1, and therefore the determinant of this flip about y-axis, when you represent it by a matrix, the determinant of that matrix is -1. Now, let's just check. For this flip about y-axis, you have the first column is the image of E1, so that's a -E1, that's a -1, 0. What's the image of E2? Well, that's E2, that's vector 0, 1. What's the determinant? Well, it's this times this minus this times this, which is exactly -1, which is exactly what we predicted. What about rotation about origin? So that is a rigid motion, so all distances are preserved, so no deformation of the space, and you do not change orientation. So you know that any rotation about origin by any angle alpha has determinant, it has a matrix, can be represented by matrix whose determinant is 1. Okay? From here, once you understand what 2x2 determinant is, you can easily generalize the very same idea to 3x3. So now, instead of having unit square over E1 and E2, now you have E1, E2, and E3, and they they form unit cube. And now, instead of areas, you talk about volumes, and change in volume, that's your measure of deformation. So now you have linear transformations in 3D. You can represent them as a matrices in similar fashion. So L of u is A times u, where now u is arbitrary 3D vector in 3D. And the determinant of the matrix is equal to, in magnitude, is equal to the deformation of volume, and the sign of that determinant is tells you whether you flipped the orientation or not. Now, orientation in 3D is a little bit more complicated, but it's really not so complicated. You can use so-called right-hand rule. So instead of having 3 points going in a circle, you actually have 4 points. And positive orientation is if you go over first 3 points in counterclockwise, and now if the fourth point is in the direction of your thumb of right hand, it's important to have right hand, that's positive orientation. But if you make the 4 vectors so that your fourth vector is pointing into opposite direction of your thumb, then that's a negative orientation. And so any rotation about any axis through the origin in 3D space, so around any line through the origin, is rigid motion, which is a special case of linear transformation. I mean, that keeps fixed the origin, and you can guess what the determinant of any rotation in 3D is. You do not deform space. You do not change orientation. So determinant of any rotation in 3D about line through the origin is 1. Okay. From here, it's not difficult to see basic. Once you understand determinant of 2x2 matrix. Now you know that 3x3 matrix is computed using 3 2x2 matrices. Well, 2x2 determinants. Well, you can decompose the volume of, now you have parallelepiped, which is the image of your unit cube, and the volume of parallelepiped can be written as a sum of 3 volumes, and now each of those volumes is base times height, and those bases are actually those determinants, those parallelograms, expressed as, areas of parallelogram expressed as those 2x2 determinants. From here, once you understand the definition and geometrical interpretation of determinants, it's easy to see basic properties. Determinant of A times B is determinant of A times determinant of B. That's so easy to see because it turns out that the product of 2 matrices represents, so it's another matrix, represents transformation which is a composition of linear transformations represented by A and B. And so if I double the area under one transformation, and then I triple the area under the other transformation, my net result is doubling and then tripling. So in total I enlarge area by a factor of 6, 2 times 3. And so that actually means the determinant of AB is determinant of A times determinant of B. And it's similar, it's not difficult to see when you flip columns. That's actually you change orientation. When you multiply one column by a scalar, that's actually like here, if you multiply, instead of having this flip, I also in addition multiply the image by a scalar, let's say factor 3.5, then I will have deformation 3.5 bigger than this unit square, and so actually you will see that other property of determinants. And also when I multiply one column by some factor and add to another column, that's also easy to see that it's actually you get the same area, the same amount of deformation. To see that, you basically you rely on the fact that if I have a parallelogram, if I choose to have some other parallelogram of the same height and the same base, so the area is the same. And that's what it boils down to, that third property of determinants. To show the determinant of A transpose is the same as determinant of A, well, that's a little that's more complicated, but then you easily get row operations rules of determinants, what you get, how determinant changes when you apply any of the three row operations. So you can just look at corresponding operations on columns, and the same will be for rows, because determinant of A is the same as determinant of A transpose. And transposing, that means rows becomes columns, columns becomes rows. So it's really nice exercise for you to see, and I encourage you to see how those rules are justified geometrically. Okay, those rules of determinants. So that will be all. I hope this was useful. I hope you learned a lot about linear transformations, how to visualize them, how to visualize matrices basically, and also how to visualize determinants. At least I hope you got a good feeling of 2 by 2 determinants. Okay, that will be all for today. Bye.